everybody. I think we can start because I don't see any other flow coming, any further flow coming. Welcome to this session about Ocular Biometrics. Before starting, I want to remind you that those involved in doctoral consortium can join the room where yesterday there was the spoofing attack experiment, right? Okay, so let's start. Our first speaker is Christian Radgeb from Hochschule Darmstadt, and he will present us a work about alignment-free cancelable iris biometric templates based on adaptive bloom filters. Please.
So thank you very much for the introduction. So the work I'm going to present has been developed together with my colleague Frank Beitinger and my supervisor Christoph Busch. So this will be the outline of my talk. I will start with a quick introduction on template protection as well as on bloom filters. Then I will describe the systems architecture in detail. I will present some experiments, draw some conclusions, and if there is time left, I will give an outlook on future work. We all know biometric characteristics are largely immutable, which causes serious threats such as identity theft, limited renewability, or a cross-matching of biometric databases. So basically, template protection schemes which are categorized as biometric crypto systems and cancelable biometrics offer solutions to this vulnerability by meeting the two major requirements of biometric information protection, namely irreversibility and unlinkability, which are defined in ISO 24745. In detail, irreversibility means that it should be infeasible to reconstruct the original biometric signal from a protected template, while in addition it should be possible to generate different versions of protected templates based on a single biometric input, and unlinkability means that it should be infeasible to cross-match such different versions of protected templates. Cancelable biometrics meet these two major requirements as they consist of intentional, repeatable distortions of biometric signals based on transform, which allow a biometric comparison in the transform domain. Based on existing literature, we know that technologies of cancelable biometrics mostly suffer from a significant decrease in biometric performance, which is mostly caused by the fact that transform templates cannot be aligned properly and local neighborhoods of features are obscured. So the contribution of this work is the proposal of a generic approach to cancelable iris biometrics based on adaptive bloom filters, where in the proposed schemes, iris codes are transformed to an alignment invariant presentation, where irreversibility is provided by the bloom filter-based transform and unlinkability is provided by incorporating application-specific secrets. At the same time, biometric performance is maintained for various configurations. To start with the basics, a bloom filter B is a simple bit array of length n, where initially all bits are set to 0. So in order to represent a set S, which consists of m different feature elements, k independent hash functions are applied to each feature element and bits at according indexes are set to 1. This means bits can be set to 1 multiple times, while only the first change has an effect. So this is what it looks like. Here we have an element x, which is hashed k times, and bits at according positions are set to 1. In order to check whether a given element y is in S, y is again hashed k times, and it is checked whether all positions are set to 1. If so, then y is in S with a certain chance of false positive. If not, y is clearly not in S. We adapt this concept in two different ways. First, we restrict to inserting exactly L elements into a bloom filter, where L is less or equal than N. Furthermore, instead of applying multiple hash functions, we restrict to applying only one trivial transform H. In conventional iris recognition systems, normalized iris textures are processed in a row-wise manner. That is, the resulting iris code can be seen as a two-dimensional feature vector, two-dimensional binary feature vector of width big W and height big H. In the proposed scheme, such a two-dimensional iris code is divided into k different blocks of equal size, where each of the k blocks consists of L columns, where one column consists exactly of small w bits, where small w is of course less or equal than the total height of the iris code. Then sequences of each column are transformed into separate Bloom filters. That is, the protected template is then represented as a set of k different Bloom filters of length n, where in our case n is 2 to the power of w, since the simple transform we employ is nothing more than mapping one column to its decimal value. That is, we set b at h of x 1, where h of x is the decimal value of the column, defined by sum 1. So here's the most important slide. As you can see, here we're processing block number 2. We have the two red marked columns. These are mapped to their decimal values, which are in this case 21 and 26. Then these values are XORed with an application-specific secret T, in this case 50, resulting in the two values 39 and 40. Then the according bits in Bloom filter number 2 are set to 1. It is important to note that the representation based on a set of Bloom filters is alignment-free to a certain degree. In iris recognition, we perform a circular bit shifting in order to align two iris codes. In case iris codes are shifted, then the majority of columns will still be mapped to the correct indexes, while columns at block boundaries may end up in neighboring blocks. However, the majority will still be mapped to the correct Bloom filters, and if columns are equal, they are also mapped to identical positions. How do we combine two Bloom filters? In conventional iris recognition systems, we calculate the fractional Hamming distance between two binary codes. Here we denote the norm of B as the amount of bits in a Bloom filter which are set to 1. Then we calculate the dissimilarity score between two Bloom filters Bi and Bj as the Hamming distance divided by the total amounts of bits which are set within both Bloom filters. So it's obviously that this score can be computed as efficient as the fractional Hamming distance. Focusing on the irreversibility of the transform, given a Bloom filter B, what we know is which columns occur in the original iris codes because of the bits which are set to 1. However, what we do not know is how often these code words occur. We only know they occur at least once, and we do not know at which locations these occur. So we need to estimate what is the amount of possible sequences which could lead to a given Bloom filter B. So we have the values, the norm of B and the amount of columns which have been mapped to the Bloom filters. Then the amount of possible sequences is defined by function f, which is applied exactly to these values. Then we calculate the total amount of sequences, which is the norm of B to the power of L, and we subtract all sequences where less columns occur, which is recursively defined by this sum applying the binomial coefficient. So here we have plotted the amount of sequences for different block sizes. Note that both scales are logarithmic, so there's really a huge amount of possible sequences which could lead to a single Bloom filter. So for instance, if 64 columns are mapped to a Bloom filter and after the mapping 16 bits are set to 1, then this would correspond to the blue curve here, and if 16 bits are set to 1, we are here, and we get a total amount of 2 to the power of 256 possible combinations which could lead to the same Bloom filter. Experiments are carried out on Casio version 3 iris database. We employ 2 different feature extractors which are publicly available in the University of Salzburg Iris Toolkit, which can be found under wavelab.at, as well as the preprocessing. In the preprocessing, the iris is detected, normalized to a rectangular iris texture of 512 times 64 pixels. Then we apply the algorithm of Masek, which employs a one-dimensional log-Gaber filter. The algorithm of Ma et al. Encodes minima and maxima within wavelength subbands. I won't go into detail. What's important is that both iris codes are of size 512 times 20 bits, where these are divided into an upper half and a lower half, since the upper half corresponds to complex and real values for Masek and bits resulting from different subbands for Ma et al. So the maximum column size will then be 10. So this is what we would call the baseline performance of the unprotected original system. So for the algorithm of Ma, at a false match rate of 0.01%, we get a 1 minus false non-match rate for Masek of around 95%, for Ma et al. Around 96%, but only if we do the alignment process. That is, we perform a circular bit shift of 8 bits in each direction. If no shifting is applied, performance decreases significantly, which is shown in the second row. Then we calculate the correlation between iris code columns. So for both algorithms, as can be seen, the correlation is here defined as 1 minus the Hamming distance, so small Hamming distance will cause high correlation. So here we have a high correlation for neighboring columns. So this is the performance of the protected system in numbers. It is important to note that the experiments for the cancelable system were performed in the stolen token scenario, so we use only one secret for the entire testing. So as can be seen for large word sizes, which would be then the column size, and small block sizes where less information about original locations is lost, performance is maintained or even improved. So for instance, for the algorithm of Ma et al., we here get a genuine acceptance rate of 98%, compared where the original systems revealed 96%. The same holds for the equal error rates. We again maintain performance or a slight decrease for some configurations. Here we have the ROC curves. Again, for small block sizes, we get a very good performance. Then we have to analyze the security of the entire approach. The security relies on the irreversibility of the transform. So we need to know how many columns are mapped to identical positions within according Bloom filters. And in addition, we have to perform an unlinkability study. So here we get the amount of columns which are remapped. So focusing on the best configuration. The best configuration would be the block size of 32 and the word size of 10, which would correspond to the leftmost right point. Note that we have different scales here. So for Masek, we would have a remapping of 48% of columns, while for Ma, we would have a remapping of 32% of the columns. So this would then correspond to 2 to the power of 126 possible sequences, and for Ma et al., this would be 2 to the power of 131 possible sequences, based on the evaluation we did before. This is the unlinkability study, so we compare the original intraclass distribution for the cancelable system using one secret to the distribution of comparing identical iris codes which are transformed with different secrets. So obviously here the dissimilarity score is even higher, so the irreversibility is achieved. This is shown for the best configuration. So in conclusion, what we presented is alignment-free cancelable iris biometrics based on adaptive Bloom filters. We have shown that the proposed transform is highly irreversible and provides an alignment-free comparison of iris codes. Experiments were conducted for 2 different feature extractors, where for both feature extractors we have shown that performance is maintained or even slightly improved. Some quick words on future work, some of which we've already done. For most configurations of the scheme for word sizes and block sizes, we achieve a compression of biometric data. So that biometric data compression would be one application. Since we do not have to perform the circular bit shifting when comparing to iris code, we can also do a computational efficient identification for protected templates, and we could also use the scheme for multi-biometric template protection, such that the Bloom filter would be some sort of container in which different features extracted from different biometric characteristics could be mapped. So this is the end of my talk. Thank you for your attention.
Can you better detail this point? Because it seems quite crucial for the results.
Yes. So this depends on the block sizes. On the configuration of the block size. If we would have only one block, then it would be totally alignment free. If we have loads of blocks, then the alignment freeness, if we can call it that way, would decrease. So this depends on how many blocks you use. The less blocks you use, the more alignment free.
On the results you presented,
yes.
When you have age limits, it seems that the protected template seems to be better in terms of accuracy than the original one.
Yes. This is a good question. So here, for instance, we get here a higher performance than here in the original case.
Any explanation how to protect? Usually when you do
Yeah.
some of them, like you expect performance
Yeah.
to be
So we expected a performance decrease, but you have to keep in mind when generating the Bloom filters, yeah, you map an entire column to the Bloom filter. So this would correspond to some sort of context-based matching because the entire column has to fit. So this is more, you're not comparing single bits here, but you're comparing entire columns here. So this, we thought of this in the same way, and we came to the conclusion that this is the cause for the performance increase, so that we have not a matching of one bit, and here we have, for instance, 6 bit at once. So this is more a context-based matching.
No other question? Okay, let's go with the second presenter. From Texas State University, and they will present the awareness detection via ocular model plant characteristics, attack of mechanical reflex.
Thank you very much for introduction. I'm very happy to be here. And let's start for the motivation for the liveness work. It can be presented by this very short movie. Oops. So this is a case of a very badly performing biometric system that accepted basically a dead sample as a live sample. And if you look at the liveness detection domain, there is a lot of work. And there is a lot of work in iris, fingerprints, and face biometrics. And I intentionally omitted the previous work, specific references, not to offend anybody who I would miss due to the space limitations. So if you are working in this area, believe me, your name is there. A few words about eye movement-driven biometrics, because this will help us to understand how we are able to identify liveness via eye movements. So the idea of eye movement biometrics is that you would ask a person to look at something. So for example, here is a text. And then based on the movements of the eye, you are able to identify who is who. And for you to understand a little bit further how this works, I would like to consciously to experience different eye movement types. We execute different eye movement types all day, basically, but we rarely consciously experience them. So let's start with the first one. The first one is called the fixation, and here I would like to ask you to look at one. So if you're looking at one, you're experiencing an eye fixation, and then the high-quality information goes to your brain. The second eye movement that you're going to experience is a saccade. Could you please look back at one, and now look at two. So you experience the rapid rotation of the eye, that is called the saccade. It is the fastest movement of the human body, 700 degrees per second. And an interesting property of this movement is that if there would be a hairy monkey running between those two dots, you would not be able to see it, just because it's that fast. Well, based on this slide, you can say, hey, eye movements are quite simple. However, it is not so. And here I wanted to show you a few examples what I called complex oculomotor behavior. To understand this information, so this is the change in the position, this is the timeline, and the target that the person has to look at changes the position like this. So this is the location of the target, and the person has to match the position of the target with the eyes. And here is the example of the undershoot, where the initial saccade executed by the person falls short of the target, and then the person needs to execute a corrective saccade to go to the target. And there are more complex events where, the person undershoots multiple times or overshoot multiple times. And in general, there are more than 10 complex oculomotor behavior events that we can see in the human visual system. And when we try to spoof the system, what we will try to do algorithmically is to program all those complex oculomotor behavior in a replica, so we would be able to simulate eye movements as accurately as possible. So the question is here, what makes eye movements possible? First of all, that's the brain that sends the neuronal control signal to what is called the oculomotor plant. And the oculomotor plant is the eye globe that is controlled by the eye muscles. There are specifically 3 pairs of muscles that are responsible for the horizontal, vertical, and torsional rotation of the eye globe. And with this replication of the eye, we are planning to attack the system. Well, you can tell me that I am working in the realm of, sort of futuristic novels, that this replication of the eye is not possible. However, this is the example where scientists from University of München are working on mechanical replica of the oculomotor plant that can execute major types of the eye. And so this idea is that you can actually replicate the eye mechanically. Well, in our case, we would like to look at a little bit simpler models. They are one-dimensional models. And we start with the Westheimer second-order model that he created in 1954. And this is a very simple model, as you can see from this diagram. So there is a rigid body, some viscous element, and passive elastic element. And it has only 2 characteristics. And so, unfortunately, it cannot model the movements very accurately. So the positional signal is not very accurate. The velocity signal is not very accurate. There are different anatomical inaccuracies that you can see here, and simulation limitations. So for example, it can only model saccades of a certain amplitude and duration. The second model that we have looked at mathematically was Robinson's fourth order model that was created in 1964. So as you can see from the diagram, it's a little bit more complex model. Unfortunately, I don't have time to go into detail, but you can see that there are many more components, modeling of mass and other forces in the oculomotor plant. And so as a result, we get very realistic positional profile, but in terms of disadvantages, we get unrealistic velocity profile. Saccade durations are not exactly normal. There are still anatomical accuracies. For example, the eye muscles are lumped together instead of being considered separately. And again, simulation limitations in a sense that the model is only able to simulate saccades from the primary eye position, eye staring straight ahead, for example, to the right. And the third model that we are considering was created by myself and my advisor as a part of my PhD dissertation. And we derived this model from the earlier work of Behill. As you can see briefly from this diagram, the model models each extraocular muscle separately, and inside of this model we have one-to-one correspondence between the model components and characteristics of the actual oculomotor plant. And this is extremely important for modeling the signal, eye movement signal, very accurately. And so as a result, we have accurate velocity profile, accurate positional profile, and accurate duration of eye movements. However, there are still disadvantages. This is a linear model and not non-linear model. And so this is a disadvantage when you start modeling saccades that are more than 50 degrees in amplitude. And here rotations are approximated as translations. So this also introduces errors for the very large saccades. But in terms of the linear models, this is one of the most accurate linear models of the oculomotor plant. And here I would like to kind of give you immediately an intermediate result, where here you can see again the positional change. This is the timeline. The changes in the position of the target are this dotted line. And the black signal is the movement of the eye, the live movement of the eye. And the gray line is what we have simulated with the model number 3. And see here you can see complex oculomotor behavior events. And so the question is, if you look at this signal, then if you eyeball the signal, that maybe after a while you are able to see the differences between the live and the spoof signal. However, we need to find out what is the algorithmic performance. This is the framework that we have presented at the last ICB that received the Best Paper Award for identifying a person based on those oculomotor plant characteristics, the invisible properties of the eye muscles, the eye globe, and the tissues. So here we have a person that is looking at the eye tracker. And in your mind, if you don't know what the eye tracker is, you can think about it as the iris recognition device, because iris recognition device is actually capable of eye tracking. And so the person is sitting here executing eye movements, and here we have eye movement classification modules that extracts those saccades. And we have a oculomotor plant model with the goal of simulating exactly the same saccade trajectories as were recorded. We have the error function that creates or measures the difference between simulated and recorded saccade trajectories, and we have the optimization algorithms that changes the parameters of the model to minimize the difference between simulated and recorded trajectories. Once the parameters or characteristics of the model are minimized, we are now working with a biometric template from which we can identify a person. So this is not liveness, this is just identification based on eye movements. Again, to reinforce what I just said, I would like to show in different picture. So this is a person reading a text. This is the raw positional signal. And the classification module marks those eye movements into saccades and fixations. And then the simulated trajectory recorded trajectory is matched by the simulated trajectory from the model. And here, this is the resulting biometrics template, and based on this template, we are going to make a decision whether the sample is live or spoof. So here is the presentation, and so we will be presenting to the system the live signal and the mechanical replicas that are simulated by the models, and based on the biometric template, we will make a decision where the sample is spoof or not. And this is most important idea and kind of the discovery of what we have realized while working on this work. The live system, the live person has very large amount of variability. And it's extremely, extremely hard to model this variability mathematically. I don't right now understand mathematically how to model it accurately. And so this is sort of the underlying principle here. If we are able to measure this variability, then we are able to make a decision about whether the system, whether the sample is spoof or a live sample. And this is how we do it algorithmically. So this is the biometric template that we have extracted from the eye movements. And we start looking at the statistical distributions of those parameters. And we start building the covariance matrices of those parameters. And then we apply PCA to create a vector of eigenvalues. And then with this vector of eigenvalues, we are matching it to the threshold. And then we can make a decision whether the sample is spoof or not. In terms of the results, the live database was collected with a very high frequency commercial eye tracking system that is very expensive, $35,000. We collected the samples from 32 subjects, 4 biometric samples per each that were collected within 2 weeks of time period. And the stimulus that we have presented to the subject was just a jumping dot of light that jumped 100 times. In the spoof scenario, we have considered 2 scenarios. Scenario A, the intruder does not have access to the biometric templates, and he creates a mechanical model, a mechanical replica of the eye based on the values that are available from the literature. And the scenario number 2 is that all biometric templates are stolen, and then the intruder has the financial capability to recreate, based on the template, the exact mathematical replica, and then present it to the system. In terms of how we tested the system, we broke the database into 2-to-1, training to testing, performed 10 cross-validation, and used the average threshold between those cross-validation to avoid overfitting. And those are results. The metrics that we are going to look at are going to be correct recognition rate, false spoof acceptance rate, and false live rejection rate at the optimal threshold, and equal error rates. As you can see, the detection rates are not perfect, but they are very high, in my opinion. And an interesting thing to think about is this, that you can see the test scenario AA and only B exists for the 3rd model. And the reason is because for the model number 1 and for the model number 2, if you start individualizing the models, they basically mathematically fall apart. The differential equations start oscillating and so on and so forth. So as we expected, and here for simplicity's sake, we can look at the equal error rate. The 3rd model with the individualized approach provided us with the highest challenge for the system. And so in terms of the conclusions, when defending attack against the mechanical replica of the eye, we got relatively high liveness detection capability. An interesting thing about, even in the case when the intruder is able to get all the templates of the people and create individual replicas of the eye, the system still performed quite well. So I would like to thank my funding, my NSF career grant, and 2 grants from NIST that fund this work. And in terms of the future work, let me advertise a little bit. So I'm looking for the postdoc to work on this. And so the goals are to improve the statistical framework and try different oculomotor plant models and look at the larger database. And here's my contact number, and I thank you very much for your attention.
Questions? I start questions.
Okay.
I wonder how much physiological conditions may alter your model. I mean, you have 4 samples for 32 individuals, right? Were such samples taken in the same time or in different times? And how much specific conditions may alter such model and increase the false live rejection rate?
I see. So this is a very good question. So in this specific case, the collection time period was 2 weeks. So 4 samples were taken in 1 day, and then 2 weeks later, 2 more samples were taken. Definitely, if you have, for example, the trauma of the eye that affects the oculomotor plant, then you have to basically re-enroll yourself, and then the templates would be very different. But again, the key, if you don't look at the eye movement identification problem, but only at the liveness problem, then this is extremely robust against the mechanical replica attack, because again, we have this variability. And we try to recreate this complex oculomotor behavior very accurately statistically. So we manually process the data, took statistics in terms of when those undershoots, overshoots occur, and try to model them. But still, again, in the mechanical system, it's extremely, extremely hard to replicate this variability, because in the human body, there is so much. So hopefully at least partially answered your question.
Your studies can be very interesting because it tries to go beyond this immediately evident in our face and in the eyes. Now, I just have a question. Did you actually try to build a mechanical system that replicates a case? The reason why I ask you is because we did it in the past. And it's quite difficult because you need acceleration, which is very high. So you need very accurate models as well, very accurate control and so on. So my question is, if you try, so if you think it's really practical, on the other hand, if you see other applications for your model.
Yes, so there are definitely, so let me start with the first question. So what I hope to prove with this line of work, that the intruders even would not try to go into the realm of mechanical replication of the eye. If you can show with a perfect mathematical model or with certain assumptions that it's infeasible to replicate, so let's say if I get to 100% recognition rate, even in the clean mathematical model, then it means that the intruder doesn't stand a chance. Because indeed, if I showed to you this mechanical replica of the eye that was created by München colleagues, but first of all, it's very hard to make, and second of all, by eyeballing again how it moves, I can see the differences. So I can detect those differences very, very quickly based on even other events, not oculomotor plant characteristics. So what I can say at the moment that is basically mathematically, I would like to prove that this is infeasible. And the second, where the research with the mathematical modeling of the eye goes, is that it has also medical implications, not only biometric, but medical implications. And in general, it's a very interesting question, and why I'm working in this area, is that psychology, neuroscience studies how similar we are as human beings, and only biometric field studies how different we are. And then mathematical models of the eye or mathematical models of the brain really try or give us the edge of understanding what are the phenomena that are underlying our differences as humans. And it's very intellectually satisfying to work on this, actually.
Please.
Thank you for your report. I have 2 questions. First of all,
Maybe one. You can meet him later.
Yes.
only one.
I'll be available at lunch. So thank you for the question. No, right now we are not considering the pupil dilation. In the sense that pupil dilation is simpler. First of all, anatomically it's guided by, well, relatively speaking, just one muscle, and then the dilation rate changes of, for example, the light. So there are less variations in terms of what can happen. Because here we have 6 extraocular muscles, and we need to account for all of them effects, where in the dilation it's sort of simpler. But to answer your question in terms of yes or no, no, we are not modeling pupil dilation here.
Thank
Okay,
you, Oleg.
thank you.
Let's welcome our third speaker. He is Xinguan Li from the University of Science and Technology of China. And he will present a feature-level solution to off-angle iris recognition.
Okay, thank you for the introduction of the session chair. I also belong to the NLPR Kasha. My teachers are Zhena Shun and Tino Tan. The title of my report is a feature-level solution to off-angle iris recognition. My name is Xinguang Li. Okay. My report is divided into 4 parts. In the first one, I will give the problem of the exciting solutions of off-angle recognition. And then our solutions is provided in part 2. In part 3, I will give some experimental results to demonstrate the validity of our solution. Finally, I briefly conclude the report. Okay, let's come to the introduction. For the practical iris recognition system, it is inevitable to encounter plenty of off-angle iris images. So we need to handle the issue to reduce the compression of the users. The off-angle is mainly caused by the gaze direction away from the optical axis. In the traditional iris recognition procedure, where the gallery sample is on angle or maybe the frontal and the probe sample is off angle. With the uniform framework, their Hamming distance is so large. It caused the forced reject. Here, green means the frontal samples and red means the off angle. Okay, for the past few years, there are many efforts to handle the issues. The most important one is to convert the off-angle iris images into the frontal one, based on the geometric calibration. The method is mainly involved with 2 steps: ellipse fitting for pupil boundary and the geometric transformation based on the ellipse parameters. And after the geometric calibration, we also do pre-processing, feature encoding, and mapping to get the final matching result. Here, we can see that the Hamming distance is improved slightly. It also caused the forced reject. Okay, so we should propose novel solutions to handle the issues. For that, let's come to our solutions. Previously, the methods such as geometric calibration and feature representation aims to make all comparisons for different off-angle categories. Here, we want to limit the comparisons in the same gaze orientations. We can summarize the idea as the divide and conquer. Here, first, I will compare our solution with the existing solutions. The difference is here and here. We add the off-angle areas classification in the processing stage to determine the off-angle categories. And then we replace the uniform feature encoding with the feature selection for specific off-angle category. For mapping, we extracted specific features of the prop sample and gallery template with the same gaze orientations. Okay, let's come to the first step, divide. Its goal is to classify the iris images into 5 categories: down, left, up, frontal, and right. Okay, the issue is how to describe the off-angle categories. In iris images, we found a phenomenon that the position of light spot is a good indicator of the category of off-angle iris images. So we should first detect the light spot first. Here, we proposed a scalable operator to detect the light spot location. After detection, we will define the geometric features of light spot. It means to describe the relationship between the light spot and the iris center. The information of the geometric feature of light spot is listed. It mainly describes the characteristics of the light spot location, the relative location from iris center, and the property of iris. Okay, let's see the SGF feature distributions. By the PCA, we reduce the dimension of SGF where the equation equal to. We can see that the features distribution are actually different for different off-angle categories. So it can be applied to classify the off-angle iris images. The off-angle iris classification problem is a multi-classes problem. Here, we transform the multi-classes problem into multiple two-classes problem. So we construct 10 classifiers and then get corresponding responses. Finally, we use the hard-working result to get the final off-angle category. Okay, let's come to the second step, conquer. We should assign the specific features to different off-angle categories. Firstly, we construct the same feature pool to cover the different features. And then I used a feature selection method to select the specific off-angle category features. And then the features is adaptive to different gaze orientations. After feature selection, we obtain the final feature representation for different off-angle categories. And in the mapping stage, we can extract the spectral features for the proper sample and the gallery template with the same gaze orientation and obtain the final Hamming distance. Okay, let's show some experimental results. We conducted the experiments on the subsite of collection iris database. We named it collection angle. The statistics of the collection angle are listed in this table. Okay, I show some example iris images. We can see that beside the frontal iris images, there are many different off-angle iris images. Okay, it's very challenging. This is the accuracy of off-angle category classification. Here we define the accuracy. That it means that the multiple off-angle categories, the accuracy. And in the training site, we use the 3,000 iris images per off-angle category, and the last off-angle iris images are used for testing. We can see that the accuracy is more than the 97. It will help to the following steps. This is the feature selection results. We can see that they share the same feature pool, and the selected features are different. The selected ordinal features are specific for off-angle categories. Different combination of three methods, including geometric calibration, off-angle classification, and feature selection, is used to demonstrate the validity of our solutions. And equal error rate and discriminant indicator are used to evaluate the recognition performance. As see, we can see that the off-angle classification improved the recognition performance largely, and we conclude that it is better to match off-angle iris image with the corresponding templates of the same category. And then we can see that if we combine the off-angle classification and the feature selection, the recognition performance is further improved. It indicates that it's better to learn category-specific other features for off-angle iris recognition. This is the corresponding ROC curves about our solution and the other method. Our solution is denoted by the black curves. We can see that it outperforms the other method. And the other method, such as the geometric calibration, means the image level. And our solution is in the feature level. Okay, let's briefly conclude the report. As the experiment showed that the classification stage improved the recognition performance largely, so it's better to use the off-angle iris image with the same gaze orientation as the gallery template. It is very helpful to the off-angle iris recognition performance improvement. And the learned specific iris features, which are adaptive to the gaze orientation, improve the off-angle iris recognition performance. Okay, in the future work, we will fusion the image level, feature level, or maybe the matching level to get more exciting results. And then I will extend my work in the no ideas iris recognition in other distortions. Oh, okay, that's all. Thank you for your attention.
Questions? Please.
So far you have shown that you can classify in 5 different classes, but the idea is just can be classified in more than 5 classes, like a half length or top length.
Yeah. We need to enroll the different gallery tablet. And
Please, maybe near to...
okay, we limited the comparison between the same categories. For example, if the probable sample is upstairs and they are not matched with the left style, because we have the off-angle classification stage and classifier before the pre-processing stage. Okay.
So you did not test some other possibilities like
Database, some other database. Okay.
I mean, your database just contains these 5 distortions, right?
Yes.
You cannot really judge what happens when you have a half-life, I direction.
Sorry.
So your database just did not contain this data, right? So that you have a top left.
Yeah.
So from
seems that you tested, I'm not familiar with these data sets to admit, but it seems that are just Oriental or Chinese eyes, or are there samples from other nationalities? The reason I'm asking is because Chinese eyes are very peculiar.
No, the database is not from Chinese.
Sorry?
The database is not from the Chinese. It is from the Clarkson University.
Yeah, so you have a sample of different countries' irises, or because the samples were just for Chinese, I think.
Okay, thank you, Matthew. The database is actually from provided by Professor Stanley Shanker's group at the University of Clarkson University. And I believe most of the subjects are American people, Western people. I'm not sure if there are any Chinese in the database. Is Stephanie here? Stephanie? Yeah, so it's really a mixture of Oriental and Western.
The reason I'm asking is because as you're tailoring your features to different position of the iris,
Yeah.
it can be the case that these features depend on the kind of iris you use, you know. But if there are different, races or countries, then it is not the case.
Yes, we extract the special features for different off-angle categories. So there is not a unified features like feature extraction stage. And for example, in the traditional iris recognition system, we after the pre-processing, we extract the uniform features, and here they are different. With the off-angle determination stage, we classify the iris image into 5 categories, and then for each off-angle categories, we extract the specific features. They are different for the other 4 categories. Okay.
Right, so what you are saying that, okay, we first classify the iris image into one of 5 classes, then we convert one of the templates, right?
Yes, we should enroll the different template. Yes.
Yeah, but if, for example, you're trying to measure it blindly to the minimum distance, i.e. you find the closest template without introducing the classification, would it be the same somehow? So it's a matter of template selection rather than introducing the classification at the recognition stage.
Yes, we can enroll the 5 off-angle categories iris image and use the minimal similarity score as the matching score. Yes. And here they are different. I think for different off-angle categories, the feature distribution are different. For example, maybe for this one here, mostly occluded by the eyelids, and we most likely extract features like these regions. Okay, this is the main idea of our features extraction stage. They are different from the traditional uniform feature extraction stage.
So my question is in terms of classification accuracy, how different is these 2 things? That's the question. Does that make, the proposal, does it make a big difference when it comes to classification accuracy from the classical way of finding the nearest template, whereby you are introducing this step to the pre-classification? I don't know whether you got the idea.
You mean the meaningless of the meaning of the of angle? Okay.
Thank you. Our last speaker is Fernando Alonso Fernandez. It's a pity for the last Fernandez. And he comes from Amsterdam University in Sweden and will present the quality factors affecting iris segmentation and matching.
Thank you very much for the introduction. Okay, so this is the traditional structure of iris.
Please, closer to the mic.
Thank you, sorry. This is the traditional architecture of a biometric system where the biometric signal is input here and travels to the whole system. And then you get here the recognition accuracy. And traditionally, when you put here bad quality signals, most works are focused on evaluating the impact here in the recognition accuracy. So the motivation for this work is to evaluate the impact directly here on the segmentation because this is the very first step of the system. So any inaccuracy here will be transmitted to the rest of the system. So even if we are able to see the effect here, we want to know what is happening here at the output. This work is motivated by a study of IREX2 evaluation in 2011, where they presented several image properties, camera and algorithm agnostic, considered to influence iris recognition accuracy. These proposed image quality components are listed here: grayscale sprite, where we expect to get better recognition if we use images with high contrast and high dynamic range; the iris size, which is the number of pixels here across the iris radius; the dilation ratio between pupil and iris; the usable iris area measured by the occlusion here and here on top and bottom; the contrast of iris boundaries, the irregularity of iris boundaries, meaning that they are not fully circular; the margin, which is the distance from the boundaries to the image edge, the focus blur, motion blur, signal to noise ratio, gaze angle, and camera interlace. In this work, we have implemented some algorithms to measure several of these image quality components. They are indicated here. They are based on algorithms already proposed, or in some of them, we have proposed here new ways of computing these quality components. To compute the focus blur, we measured the amount of high-frequency components using a convolution kernel. This quality component is computed both globally in the whole image and locally around the pupil and sclera boundaries only. The motion blur interlace is computed by measuring the difference between two adjacent rows of the image based on a study proposed in 2006. This is also computed globally in the whole image and locally around the pupil and sclera boundaries only. For the computation of the circularity of iris boundaries, we extract here in green is shown the detected circle of the boundary, and we regularize the iris contour, so we detect in red the through boundary, and we compute the distance between the detected and the regularized contour. And this distance average across the whole boundary is used to measure the circularity of the boundary. Of course, this can only be computed locally on the pupil and sclera boundaries. We also compute the contrast of iris boundaries using two different measures. One is the iris edge sharpness proposed in this paper. In this measure, we position at two equidistant points around the iris boundary, and we compute the difference in gray levels between these two equidistant points, and this is done for the whole circle. So we get a measure of the contrast in the boundary. And we also use the orientation certainty level proposed in this paper originally for fingerprints. And this measures the energy concentration among the dominant direction in a local neighborhood, and is measured using intensity gradients. Here we can see two examples of these two measures here of iris edge sharpness and the orientation certainty level. Here we can see the value of this measure at the blocks around the boundary, and we average this measure around the whole boundary. This is only computed locally, of course, and We also measure the grayscale spread using two measures here, the skewness of the image. This measures the histogram asymmetry, so a value of 0 means that the histogram is symmetric. If it's negative, the histogram is moved to the right, so the image has higher gray values. It can be seen here. If the value is positive, the histogram is moved to the left, so the image has lower gray values. We use here the absolute value, so we measure the symmetry of the histogram versus the non-symmetry of the histogram only. And as a second measure, we use the standard deviation of gray values, normalized by the mean for luminosity independence. These two measures are computed globally in the whole image and also locally around the pupil and scleral boundaries only. Here you can see some examples of these two images, of these two quality components, sorry. And the last quality measure that we have implemented is the occlusion, or the usable boundary, measured as the percentage of non-occluded boundary when the boundary is modeled by a circle. And of course, this is only computed locally. To summarize, we have 8 quality components. All of them are computed locally around the iris boundaries, and 4 of them also are computed globally, which is in the whole image. For the experiments, we use the Biosec baseline database, which more than 3,000 iris images, acquired using an LG close-up scanner with LED illumination positioned to ensure that reflections fall inside the pupil. And this sensor also incorporates some check of subject positioning and distance to ensure that the images are focused in some way, and also it selects the best image of a 20 frames video, so it already incorporates some kind of quality selection. We have manually annotated the iris images, so we have annotated both the circles of the iris, and we have also annotated the eyelid's position, at least here and here, modeled by a circle, so we get here the mask of the iris region. We plan to make public this ground truth in our database, so you can check the database of my laboratory, or you can send me an email directly. For the iris segmentation, we use our own segmentator based on the generalized structure tensor, which has been proposed recently. This segmentator is based on the use of circular complex filters encoding the orientation of the expected orientation of the boundary. This filter is convolved with a derivative image of the iris obtained from gradients here. So when the radius of this filter is the same than the radius of the target circle, then we get a maximum in this convolution in the center of the circle. So using this procedure, we are able to extract the two iris boundaries here. We also do matching experiments using log-Gabor wavelets matcher based on unwrapping the iris region to a rectangular shape, and then applying log-Gabor filtering and binary quantization. And we also use the SIF operator adapted to work with iris images. So here it works directly on the iris image, it is not based on unwrapping. So directly here we detect SIF points and do the matching between different images. To evaluate the segmentation accuracy, we compute this distance here between the detected circle, which is plotted here in green color, and the annotated circle, which is plotted here in black color. So this maximum offset is used as the measure of segmentation accuracy, and is normalized by R, the radius of the annotated circle, for size and dilation invariance. So if this epsilon here is equal to R, then the distance, or the normalized distance, is equal to 1. So we obtain invariance to these two factors. These are the box plots of the 8 quality measures that we have computed in this work. In some of them, as you can see here, we have both the quality measure in the pupil and the scleral boundaries, and also in the whole image. So some remarkable things here is, for instance, that there is less blur in the whole image, so we have a different measure of blur if we compute in the whole image or in the boundaries only. There is more motion in the pupil boundary, more gray variability in the pupil boundary, zero skewness in the iris boundary, so the histogram is symmetric in this region, but the image shows, the database shows brighter gray values in the whole image on average. And in this database, the occlusion affects mostly to the sclera, not to the pupil boundary. To evaluate the impact of quality components on the segmentation, we classified the image into 3 equal quality groups based on each measure. We report the segmentation accuracy for each group, both using global and local quality measures. And local measures are computed around the annotated boundaries. This is one of the drawbacks of this study. But we intend to reveal the source of segmentation error, not to say, and so we cannot rely on a segmentator that maybe is not 100% accurate. So this is why we compute the local quality measures using the annotation. Sorry for this dense slide. I will summarize the most important things. Here we have the segmentation accuracy using the global and the local quality measures. Remember that we have 4 quality measures, 4 global quality measures. So for each quality measure, we have the segmentation accuracy in the pupil and in the sclera. And we have 8 quality measures here. So for each measure, we have 2 results, one for the pupil and one for the sclera. The most important thing that we have observed is that local quality metrics in general are better predictors, meaning that the slope here, as we move from low quality to high quality images, if we use global quality measures, this slope is not as pronounced as here when we have local quality measures. For instance, here and here, you can see that this slope is higher than using global measures. It's also remarkable that some measures have opposite behavior when they are computed globally or locally. So here, for instance, the segmentation performance goes that way, and using the same measure but locally, the performance goes the opposite way. Concerning local quality measures only, I have marked in blue the best predictors for pupil segmentation, and in green, the best predictors for sclera segmentation. We have used a circular segmentator, so obviously the measure of circularity is on top, or neatly on top. And this is also a iris segmentator based on edge detection, so the 2 measures of edge contrast are also on top. And concerning the sclera, the most important factor affecting the performance of the segmentation is the occlusion. So this is a remarkable result here. This is not affecting the pupil because in our database the pupil is not too much affected by occlusion, but for the case of the sclera, this is the factor impacting the most the segmentation. We also study the impact of quality components on the matching. We also classify the database into 3 equal size groups, but in this case based on the quality of the score, not the image. The quality of the score is defined as the average of the quality of the 2 input images. Using global quality measure, if we compare the impact on segmentation here and the impact on recognition rates, we observe, for instance, that there is no correlation between the behavior in segmentation and the behavior in the equal error rate. Here we can see that the segmentation performance improves in some way in this direction, but here we don't see the same behavior. If we focus on local quality measures, what we see is that we observe a tendency, the same tendency seen in the segmentation. In the segmentation, we observe that the segmentation performance improves in this direction mostly, and here we can also see that the equal error rate improves in the same direction. Interestingly, using the SIF matcher, this matcher is less sensitive to variations in local quality, even if the images in the quality groups are the same for the 2 matchers. So a bad segmentation does not worsen the equal error rate using the SIF matcher, but a good segmentation doesn't improve either the results. So So we observe here that there is not always correlation between performance in the segmentation and performance in recognition. So to summarize, we have evaluated the impact of several image quality components in the performance of iris segmentation. We compute quality locally around the boundaries, and in some cases we also compute quality globally. Local quality metrics are better predictors of segmentation performance, and some measures behave differently when computed locally or globally. We also evaluate the impact on the performance of two matchers based on log gather and shift. Matchers are also sensitive to quality variations, but not necessarily in the same way than the segmentator. And the shift matcher is more resilient to segmentation inaccuracies, so errors in the segmentation may be hidden by the matcher, by this particular matcher. So here we remark the importance of measuring the precision of iris segmentation also, not only looking into the matching accuracy. As future work, we have observed that that the quality measures are not necessarily correlated. It's not shown in this study. And quality is also multidimensional, affected by several factors that we have seen in this study. So we plan to fuse the estimated measures. We obtain a single measure with higher prediction capability of the segmentation and matching accuracy. And also based on the different sensitivity that we have observed in the matchers, we plan to improve matching performance by using adaptive quality-based fusion scheme. So this is the end of the presentation. Thank you very much for your attention.
Questions?
Well, thank you for a very interesting presentation. If you go back to the very last slide. Okay, so the last one, very last one.
Oh, that one.
Very last one. Okay, so some preliminary experiments show that coordination are not necessarily correlated. I'm not sure whether correlated or independent.
Yeah, I mean correlated. I mean, maybe you have blur, but you don't have other kind of.
Other places on the list of the measurement is up here. I think some of them are not really general, because some of them, for example, the measure of singularity is clearly algorithm dependent. For example, if the iris segmentation algorithm does not assume a circular value, then this measure is obviously irrelevant. Correct?
Yeah.
So they're not very general.
Yeah.
So
Okay.
they are really algorithm dependent.
Yeah, of course. Right. What I mean is that maybe we can combine in some way, because you can have one and maybe not the other perturbation at the same time. This is what I mean.
You used a sex algorithm for matching experiments. I think it's not the state of the art iris matching algorithm. Why did you use the state of the art matching in your experiments? That's why you get the conclusion that the shift matching is kind of better than the other matching, right?
Yeah, I cannot hear you very much.
I said you used a sex algorithm for matching.
Yeah.
Right? Yeah, which is like 2003. It is not the state-of-the-art algorithm. So
No.
why don't you use a state-of-the-art algorithm in your experiments? I mean, the conclusions you draw are probably based on an obsolete algorithm. So, I mean, what benefit do we have from the results?
Yeah, well, we have used, in one case, we have used an available algorithm based on log gather. It's not maybe the state of the art, but it's widely used because it's available. I mean, and in the other case, we propose the use of shift for iris matching, so we have made use of what is available.
Why not use a state-of-the-art iris matcher just for the experiments, like very eye?
What is, you mean?
I mean, why don't you use a state-of-the-art iris matcher for experiments, like we have very eye, which is easily available?
Well, what is the state of the art?
And the other question I had was on the segmentation, where you essentially, I think he had the same question. Like, I think there are better segmentation methods available which use like active contours for segmenting the pupil from the iris image.
Yeah.
You are using a very basic circular model. So I don't know if your results would basically.
Yeah, we have started with circular segmentation, and Also, non-circular methods for cementation have some kind of circular fitment in some way. So we have started with this. We also plan to move to non-angle images. We have not included here not angle, so we plan also to consider this kind of segmentation also.
Okay, thank you. Sorry, you will meet the author later because we have to leave place to the poster presentation. So thank you for attending the session. I remind you that the doctoral consortium is in the room where the spoofing attack evaluation was yesterday.